Hi, I'm Zor. Welcome to Unizor Education. So we continue talking about Lagrangian. Today's lecture is about Lagrangian in Cartesian dimensions. Now, this lecture is part of the course called Physics Plus for all. It's presented on Unizor.com. The website is totally free. You don't have to sign in, you don't have to subscribe. There are no advertisements, so it's really totally free and nothing prevents you from studying. So please do. Knowledge is power. Okay, so last lectures in the course of Physics Plus were about Lagrangian. Lagrangian mechanics is kind of not a replacement, but it's a different view to the same problems Newtonian mechanics was developed. So Newtonian mechanics, basically quintessential of Newtonian mechanics is second Newton's law, which is basically the force is equal to mass times acceleration. Now the problem is that in simple cases this is simple, but in more complicated cases, let's say you're talking about solar system. So we have planets and we have sun, and all of them gravitate to each other. So there are many different objects which exert the forces onto each other. So there are many different forces, and they're all vectors. You have to really sum them up. If you want to know how one particular planet, let's say, is moving, you have to sum up all the forces, vector forces from all other planets and from the sun. So it's not easy. Lagrangian gives you a little bit better approach in a way that it deals with energy. Energy is scalar, so that's why it's kind of easier. And there are some other advantages. Okay, so let's talk about one thing at a time. First of all, let me remind you that I have first introduced the concept of Lagrangian a couple of lectures ago when we were talking about springs. So if you have a spring and there is an object which is going back and forth on a spring, it's very easy to approach this from Newtonian, second law of Newton. But as an illustration, I did exactly the same using Lagrangian. I introduced Lagrangian as difference between kinetic energy and potential energy, and it looks like Lagrangian's approach, which is using Euler-Lagrange equation, which we also discussed before, gives the same result. It's equivalent. So my purpose right now is to do this type of to prove the equivalency of Lagrangian approach and second law of Newton for n-dimensional Cartesian coordinate system. So that's basically my lecture for today. So we have many dimensional problem, like for instance planets of solar system. They are all kind of interacting with conservative forces, and Lagrangian approach will give you, I would say, a little faster and simpler equations, which you still have to solve. I mean, these are differential equations of the second order relative to position, because acceleration is the second derivative of the position. So it's still second order differential equations, and there are system, actually, there is a system of these equations because there are many different objects, so you have to basically have it for each coordinate of each system. But in any case, Lagrangian seems to be giving a simpler approach, and that's what I'm going to do today. Okay. Now, again, as an illustration of Lagrangian, I had another problem, more difficult problem, the problem of a spring pendulum. So there is a pendulum, but this is not fixed. This is a spring, so it can actually be squeezing and stretching the spring, and at the same time rocking back and forth. Now this is more difficult problem, even for Newtonian mechanics, but with Lagrangian it seems to be getting a faster results based on energies. So again, Lagrangian is the difference between kinetic and potential energy, and this is for all the systems, whatever we were talking about. Okay, now next thing is, I do recommend you to refresh all your knowledge about conservative forces, about the fields like gravitation field or electrostatic field, which actually produce these which is gravitational or electrostatic forces, which are conservative. So conservative means that if you have two different positions, beginning position and ending position of the object, and it moves by different forces, and these forces are conservatives, so the work which performed by these forces, the moving from A to B, is independent of the trajectory. So we did discuss this, and I assume that all these issues are supposed to be known, because this lecture is using it very extensively. And what's probably the most important thing is that there is a concept of potential, and the force, if it's a conservative force, is basically can be expressed as nabla, which is differentiation by coordinates of the potential. Potential is a scalar, so potential is a function of vector of position. Now, force is also force is the vector. So this is vector of position, this is vector of force. And nabla is an operation which means that x coordinate of the force is equal to minus d per dx of u, y coordinate is equal to minus g per dy of u, and z coordinates is minus d per du per dz of u. So these are partial derivatives. Again, all these concepts are in the courses which precede this one. So that's why it's very important to take whatever I'm talking about as a course, not as an individual lecture. If you just found somewhere on YouTube, you do have to know all these things. So I assume that we do know about this, we do know about the potential. If it's a field, for example, that's the potential of the field, which is related to the distance. Let's say if it's a gravitation field of one particular source, then it's proportional to 1 over distance to the source. And if you will take a derivative from this, you will have minus 1 over r square, and again r square is in the denominator. That's how gravitational forces are actually working. It's mass times mass of the source times mass of the object and gravitational constant. So the same thing is here. So as you see, in gravitational cases it's very simply, and it's really indeed, if you will take a derivative of potential, which is r is a distance between the source and the object, then you will get the force. If you will have electrostatic field, that's the same thing. If you will take, let's say, a spring, now in the spring case, your potential, if you just squeeze the spring by certain lengths, then the potential would be, I think, this one, where r is the distance of squeeze. If you will take the derivative of this, like this one, you will have kr. K is elasticity, and r is basically the distance you're squeezing. So this is the force. Force is with a minus sign, obviously. Force is by the magnitude is proportional to distance you're squeezing the spring. So in all these cases, all these forces are conservative and they satisfy all these equations. So these are just examples that we were talking about before. And right now, all I'm saying, all I would like to talk about today is the equivalency between Newtonian approach and using the Lagrangian, in case you have a closed system with stationary forces in between. Like, for example, our solar system, where only the stationary forces of gravitation are acting between. Okay, fine. So that's done. Okay, now let's assume we have a system of n point masses. So you have n point masses in three-dimensional case. Now, the position of this system is described by n three-dimensional vectors of position, right? So you have basically R1, R2, etc., Rn. All of them are vectors, which means all of them are triplets x2, y2, z2, etc., xn, yn, zn. So all these 3 times n parameters describe the position of all n objects in our system. All right? Okay. Now, if we are talking about stationary stationary forces depend only on position, which means every force which is acting on object number I depends on all of those, on all 3 n parameters, every force. And every force can be represented as minus nabla, I will put nabla I, of potential of the, in this case maybe a gravitational field or whatever other source of the forces is. Now, what it means is nabla I means it's a vector. If d by dx I d of dy I and d by dzy of potential. So this is the vector and this is the vector of 3 components. Well, I probably can just write it this way. I'll put it you here, and you here. So this is the vector. 3 components here, 3 components there. So I assume that this is kind of a known thing, and because forces are conservatives, we can do this, and U is potential, which is basically potential energy at every point. U obviously also depends of all the position of all our n vectors. So as soon as position is known, which means all these vectors are known, at any point in space we can determine, based on this function, basically it determines a scalar which is a potential of this field at this particular point. Okay, and from this, using the partial derivatives by i's coordinates, we can get the force which is acting on i's object. So, in this particular Newtonian equation, where f and a are actually vectors in 3-dimensional field, well, actually it's fi for i's object, but there are these type of equations are supposed to be for each object, right? So we have n objects and we have n vector differential equations, which means we have 3n, because it's for each coordinate. It's f I x is equal to m a I x y and z at the same time by each coordinate, because forces and accelerations are vectors. Okay, so we have the same basically number of differential equations, but the problem is that in this case, for solving all these equations, for x, y, and z of each object, you need all forces. Now, all forces is kind of a difficult thing because they're all vectors. You have to add the vectors, which means you have to do it coordinate by coordinate. It's kind of difficult. In this case, in case if we are talking about using Lagrangian, which depends on energies, kinetic minus potential. Potential energy is a scalar. So if you have a distribution in space of all these objects, you basically can relatively easy calculate what is the potential in each point. Well, for example, if it's a gravitation, all you need is a distance from this point, which you would like to determine your potential, to all other, and use the law of gravitation. And then, since potential energy is additive, you just add this like scalars. So you have basically n different components, you add them together, and you have potential at each point. So that's kind of easier, which means that this thing in the Newtonian second law, we can determine basically based on potential. Again, all I'm saying right now is that you can get the same results just doing a little bit simpler approach. How about acceleration? Well, acceleration we will derive from kinetic energy, and here is how. Now, kinetic energy of, let's say, ice object is 1/2 mass times speed square. This is speed along the trajectory. So this is kinetic I. Now, what's very easy to do is to differentiate it, partially differentiate it by I. So dki by dvi. Well, instead of dvi, I will use, this is the speed, right? So I can use, well, speed is a vector, but I can actually do it by coordinate. I can do it by xi derivative, and correspondingly k by y I derivative, and ki by z derivative. So x derivative, y derivative, and z derivative are components of speed, right? Alright, so what will be if I will differentiate this by v? Well, that would be 1/2, and then 2, it would be m vi, right? So this is a dk by dvi. Okay, what if I will differentiate it again? Differentiation of speed is acceleration, right? So one more thing. So, but now I will differentiate it by time. So this is differentiation by vi. So it's a partial differentiation by vi. So time is not involved. But now I would like to convert speed into acceleration, and that's why I will have differentiation by time of ki by vi, and that would be MAI, right? Because differentiation by time of this is MVI, so we will have MAI differentiation. And this is exactly this part. Again, we can do it by coordinates, but doesn't really matter right now. Basically, what we have come up with is the following. That I can replace this with basically minus d minus nabla I of u. And I can replace this, the right part, as d by dt of dki by dvi or I can actually put, instead of dvi, I can put r vector ri, which basically maybe is a little bit better if I will just put by coordinates, minus d by dx u is equal d by dt d by xi's dki by dxi derivative. So that's how it would look by coordinate. Same thing by y here, and same thing by z here and here. Okay, so basically that's it. However, I can just make a little bit more, well, algebraic tricks, if you wish, to look better. Actually, it will look much better than this one. Not much, but a little bit better. Here is the problem. Now, I don't like that this is a Ki. It's a kinetic energy of one particular object out of n. U is a potential of the whole system at point where xi is located, right? So I would like everything to be like a complete energy of an entire system. So this is complete energy. This is energy of one particular object. I would like to change it to complete energy. And what I will do just this. Why? Because there is no difference. Look, K is basically K1 plus K2 plus etc. plus Kn. Kinetic energy of the entire system is a sum of kinetic energies of components. Now this one depends on the speed of the first object. This one depends on the speed of the second. This one depends on the speed of nth. So if I'm partially differentiating by speed of the ith component, then these, everything which is not I, so only Ki would contain di. Everything else do not, which means if I will partially differentiate it by vi, these are completely irrelevant. They're constant. It's a partial differentiation by one particular parameter. So that's why I can put, instead of Ki, I can put an entire K, which is the same, which is energy of an entire system, just because I'm doing this partial differentiation by the speed of the ith object. And all other kinetic energy of other objects do not depend on it, and partial differentiation would give 0. So that's first thing. It's kind of convenient. Okay, so now I don't have any indices of I in energy parameters. So this is the total kinetic energy of the system. This is total potential energy of the system as they are in existence at any particular moment, at any particular position. Because as soon as you change the position, so U and K both are function of all position. vectors, and k the same thing. Depends on speeds of every object. So as soon as I do some change, both things are changing. Because I'm changing position, u is changing. Because I'm changing speeds, or velocities rather, my kinetic energy is changing. Okay, so one more very little trick. So instead of using k and u, I will use Lagrangian, which is k minus u. Now let's just think about it. K depends only on the velocities, and I'm actually differentiating u by positions. So if instead of here u, I will put L without minus. If I will put dl by dxi. So if L is k minus u, differentiation of k by position is 0, because kinetic energy doesn't depend on position, it depends only on the speed, on velocities. So that would be exactly the same as this. So instead of this, I will use this. Now, what if instead of k, I will put again L? Same thing. Since my L is equal to k minus u, differentiation by k would be the same, and differentiation by u does not depend, potential does not depend on the velocity. Potential depends only on positions. So there is no dependency on this. So if I will consider function L, which depends on all r and all r derivative, well, which basically means this is x, y, z, this is x, y, z first and end, this is also x, the derivative by x1, derivative by time, etc., etc. Then I will have basically this equation, and this is basically the Euler-Lagrange equation. Now, my point is that this is equivalent to this and this is equivalent to that. That's it. So I have basically derived a different equation which looks differently, looks actually more complicated, quite frankly, than this. But it's simpler because L is just one particular function which depends on 3n and 3n, depends on 6n parameters, which is a combination of kinetic and potential energy, which are scalars, which means we can completely differently calculate this total energy based on all these parameters. It's actually easy to calculate Lagrangian, which is k minus u, kinetic minus potential, if you have all these parameters. So these parameters are like supposed to be given. Like, okay, the position of the system is such. You have all the position of all the objects and all the speeds in all the direction, all the coordinate systems. And as soon as this is known, the calculation, let's say it's a gravitation field. Well, if you know the all vectors of positions and all vectors of velocities, to calculate kinetic energy and potential energy is basically kind of a known thing. And that's it. So you have this particular equation, and it's the same equation if you will have an integral from t1 to t2, L of t dt, and you have to minimize it. Remember this from variations? So the solution is that it minimizes the trajectory, is minimizing the Lagrangian, the integral of Lagrangian, which is called the action. So minimization of the action is actually the way how trajectory is going on. So that's what's very important. So you have this one function, Lagrangian, of all these parameters. And if you would like to know how the system is changing its position from one point to another, well, you have to calculate this action integral, and minimization of this gives you the Euler-Lagrange equation. Well, that's it for today. Thank you very much, and read the notes for this lecture. That's very important. Okay, thanks. Bye-bye.